Welcome back to Orgo 2. Dr. Schoffer speaking here. Next up in Chapter 18 is the discussion of nitration. So first of all, I think it's very important for us to recognize what the conditions are for a nitration reaction. And sometimes it's confusing for students to see two very strong acids here. The way we need to think about these conditions, the use of nitric acid in the presence of sulfuric acid, is that this will generate the very potent electrophile. And that sulfuric acid here is an acid catalyst. In other words, it will offer an H+. So the essential ingredients are really nitric acid and a proton source, and a strong enough acid here is then given through sulfuric acid. That is not to be confused with the sulfonation reaction, which is H2SO4 enriched with SO3, as discussed before. So when we have these conditions here, we're also forming this very potent nitronium ion. Please be familiar with the structure and its name. So one question I have for you now, and you could pause the video here. Do you know how to draw a Lewis structure? Meaning, can you draw all the bonds and place the charge correctly? I would also offer at this point that if you have trouble promptly drawing a structure like this, you might have to go back to Chapter 2, where molecular representations were discussed. And I think also in Chapter 1, you need to be able to place formal charges and understand how these ions are formed. Now, what's the Lewis structure of this? Again, you can pause and try to actually formulate that and then think about why this would be a very, very potent electrophile. So we've used a placeholder for electrophile, referred to as E+. So we see the mechanism on this slide. Here is a good Lewis structure of nitric acid, and here we see what essentially is a net proton transfer reaction. So sulfuric acid is there to add, so this is a net addition of one proton, one H+. And even though this looks unusual, this is the Lewis structure in which the octet rule is obeyed for all the atoms, even though it involves charges, adjacent charges, but this is the appropriate Lewis structure for nitric acid. We have a positive charge on nitrogen, a negative charge on oxygen. And how now this hydroxyl group, or H group, is picking up a proton, and here you see the outcome. So one lone pair was now converted into a bond with hydrogen, and this now sets this up perfectly as a leaving group. So this, you might remember all the substitution reactions you discussed in Orgo 1, where we had to create a good leaving group to then expel it. And through the loss of water, we now have access to the nitronium ion. So this should be your correct answer for coming up with a good structure here. So this is your active electrophile, and that can be used in the mechanism which is described on the next slide. The nitration of benzene. So all the hydrogens are equivalent. We could use any of the double bonds. As written here, you pick one of the double bonds and you need to start it appropriately in between the two atoms that are sharing that double bond. This will now, instead of a pi bond, will make a single bond to NO2, and we know that nitrogen can only have 4 bonds in this scenario, so we're going to have to break one bond to oxygen. And that's how we come up with basically it is summarized in here, but remember there's a positive charge on the nitrogen and a negative charge on one of the oxygens, and you may want to practice drawing this fully out. So the aromatic ring acts as a nucleophile that now forms the sigma complex as shown here. So we can also use the letter sigma. And what's unique about this is that we can formulate at least 3, sometimes even more resonance forms, and we can assess the stability. And what we see here is that the positive charge is doubly allylic, so to speak, We can move it around. Please be familiar with this, and that whether we use this structure or this structure, we can then expel that proton that is being replaced. Remember, we're dealing with a substitution reaction, and so here we have one hydrogen, or the proton, being replaced with NO2. So we need something basic in the mixture. So in this case, we could just use the water molecule because we're dealing with an aqueous solution having nitric acid and sulfuric acid. And this will now pick up the proton that now reestablishes that double bond and therefore restores the aromaticity. Now, a nitro group can be reduced to form an amine. So not only do we learn about substitution reactions in here, but also about additional synthetic methods that help essentially expand the synthetic toolbox of functionalizing structures. So what we see described here is the nitro group. This is a nitrogen with 2 bonds to oxygen. These are replaced with 2 bonds to hydrogen. So this is a reduction reaction. And the typical reagents that we use are either iron or zinc in the presence of HCl, followed by a second step that is basic. I wouldn't be concerned with the mechanism here, but please recognize these reaction conditions for the functionalization. So as we combine these reactions, we basically now have a process to go from our hydrogen. So one of these hydrogens is being replaced. We just line up all the conditions. This is the nitration reaction, the reduction and workup under basic conditions, quenching the acid here as well, or neutralizing the acid. And that now installs an amino group. And as said many times before, and I might sound like a broken record, but please practice to make sure you know the skills and integrate them into your notes. You can pause the video here and look at some of the checkpoints and then insert them into your notes, one or a couple of homework assignments to help you with a more effective and efficient review later on as we're heading towards accumulated final exam. Now, another procedure for functionalizing a benzene ring is a named reaction. It is the Friedel-Crafts alkylation. And as the word says, we're introducing an alkyl group. So in this case, we're now replacing one of the hydrogens on benzene with, here's our alkyl group. So this is a sec-butyl chloride. This happens in the presence of aluminum trichloride, which is a Lewis acid. It plays the role of a catalyst in this reaction. So what you see is that one of the lone pairs can attack the aluminum in AlCl3. We're basically forming a Lewis-base Lewis acid complex, which is shown here. This now gives aluminum extra electrons and places a positive charge on the chlorine, which sets this up for a better leaving group. And here's your effective electrophile. Remember, we use E+ as a placeholder. So now this is going to be more effective in this mechanism. You should become more comfortable in describing these mechanisms using the roles of nucleophiles, electrophiles, and good curved arrows with clarity and sufficient detail. Here we have a summary as we are replacing that hydrogen with the alkyl group. We do have some side products. In organic chemistry, we are less concerned with stoichiometry compared to general chemistry, and mostly very much focused on the overall conversion, how a functional group changes from just having a carbon-hydrogen bond on the benzene ring to now having a carbon bond to an alkyl group, which we can generally abbreviate as R with a placeholder. Similarly to what we saw before, these mechanisms have a lot of parallels. Aromatic ring is the nucleophile attacking the electrophile. Here's the E+. forming a sigma complex. There will be at least 3 resonance forms. And then we have the abstraction of the proton that restores aromaticity. You can pause here again and practice this with a couple of questions and see whether you understand this fully. On this slide here, some comments about the efficacy of alkylation reactions, Friedel-Crafts alkylation reactions. Simple primary halides can be used effectively. We do form this complex, but it is also stated here that these primary carbocations cannot really form in the way we sometimes describe them. They're not stable. We prefer tertiary cations, but then we would make different products. So in this book, and they're being consistent with this, they're using this complex. So again, this would be a Lewis base and a Lewis acid complex. So instead of drawing just an ethyl cation, which I'm showing here as a skeletal drawing, this is now associated with having the chlorine still on there that is bonded to the aluminum. Okay, let's practice something. So you may want to pause here and take your time. So identify the product that forms when benzene reacts with T-butyl chloride in the presence of aluminum chloride. Go ahead, analyze the conditions, maybe formulate a mechanism. I will switch over to my ChemDraw program. All right, so here's the question. It's easier for me to draw in here. Identify the product that forms when benzene reacts with T-butyl chloride. So first, as I said before, it's much more helpful to have a mechanistic understanding so you can derive the answer rather than just using rote memorization to just recall the structure and not having a sense as to why certain things happen the way they are described. So what I'd like to do is, and I pre-drew some structures here. So here's the T-butyl chloride. I'm just going to pull this down. So as we're analyzing the structure, and maybe I'm going to enlarge this a little bit. All right, so this is a tertiary carbon. We have methyl groups all around. You can draw them out or not. In my program, I can show them or leave them out. So this would be, let me see, I need to go into a different mode. Let me erase this real quick. All right. So I'm filling in the methyl groups. If you want to draw a C, you can do that. So this would be a more complete structure if this helps you with the bonding patterns. If we now get rid of the chlorine, I'm just going to copy over the structure. And then I erase that bond to chlorine. What would be my electrophile that is formed in here? The program already automatically fills this in, but I'm telling it, no, this really is just a carbon, and then I have to add my charge because we lost an electron in here. And this is our potent electrophile. So we now have the benzene ring reacting with this. So in the presence of benzene and having aluminum chloride, the structure that you obtain looks like this. So we have the bond to carbon, and then I need to add 3 methyl groups. So this is the skeletal drawing. This would be a product, and I can copy this over and then paste it into the slide. Okay. Again, it would be helpful for you to practice the mechanisms. Since practice is good for us, let's try something else. What is or are the product or the products when benzene reacts with butyl chloride in the presence of aluminum chloride? Again, you may want to pause right here. Think this out. Can you formulate a mechanism? What's the nucleophile? What's the electrophile in the part? And will you get 1 or 2 products? Can you deduce that? I'm moving on to the next slide where I'm actually giving you some more insight into the mechanism and what is happening. So one of the key aspects for Friedel-Crafts alkylation is that when we're dealing with primary halides, that we can have rearrangements. If this concept is confusing to you, then I would encourage you to go back to chapter 6, where rearrangement reactions were introduced. Okay, so a mechanistic understanding is really important for succeeding in Orgo 2, and we need to practice that now. So this was chapter 6, I believe was point 7 to 12, have all the important discussions about mechanisms. If you are stuck here, you really are wasting your time moving further ahead without addressing some of maybe the lacking skills or the confusion that you have here. So let's go back to this example. We have a primary halide. We said that we don't really want to draw just the carbocation here, which is a primary carbocation, and as described before, that this is more of a complex, and that complex is actually shown here. So I'm going to put this in square brackets. What is now possible to happen is to go from having, instead of a primary carbocation, to generate a secondary carbocation, which we can also describe as 2-not. And this happens by having an adjacent hydrogen. So we recognize that there are two hydrogens. We only need to pick one of them. And both of these electrons move over. And now one hydrogen is embedded in the methyl group that's here. We don't have to show it. And that now, because we took electron density away from this carbon, we now have that other carbocation. And sure enough, we see that we have both the reaction with this complex, with net transfer of this primary carbocation, but that's going to be the minor component, and that this now indicates that this pathway is really preferred because it generates a more stable intermediate, and therefore you have this as the majority product as you're making a bond to the second carbon. Here are some examples where you can practice those skills. There are some things that are not helpful with the Friedel-Crafts alkylation, and here are several limitations mentioned. So we have to make sure that the halide leaving group is attached to an sp3 hybridized carbon. And here are the examples of where we cannot apply the Friedel-Crafts alkylation. Later on, we learned that we can use organometallic chemistry to accomplish this, but not under the Friedel-Crafts reaction setup. What you see here is our benzene with the intent to replace one of the hydrogens with an alkyl group. But what do these two have in common? Both of them actually have sp2 hybridized carbons here. If you don't understand this, you need to go back and understand hybridization, which is in one of the earlier chapters described. Another thing that is frustrating is that once we replace one hydrogen with an R group, so this now will then become an R in, attached to the phenyl ring. So I'm just going to use an abbreviation. When we assess reactivity, scientists observe that when we do such a reaction, this actually, the T-butyl group or this R group has an electron donating effect on the phenyl ring. So EDG is what I'm trying to write here. And it does this through induction. It's a weaker effect. It's not as strong as resonance, but still it activates the ring. If the ring is activated, it will speed up the reaction. And then what we see is polyalkylation. So you may have not only one T-butyl group, but a second one. Because of bulkiness, it won't happen here, but it could happen with other alkyl substituents. Now, some substituted aromatic rings, such as nitrobenzene, are too deactivated because the nitro group, takes electron density out of the ring. Remember, we had this very unusual bonding pattern. in which nitrogen can only have a maximum of 4 bonds, and that we have a negative charge on one of the oxygens, a positive charge on the nitrogen, and this is ready to take out electron density, and it would be best to also fill in the non-bonding electrons, so it looks a bit crooked, but I think you understand what I'm trying to communicate here. So Friedel-Crafts alkylation reactions are not suitable for deactivated substrates, starting materials such as nitrobenzene. And actually, I'm surprised that the numbering here changed, but let's just move on. We can also observe rearrangements, as was shown on the previous slide. And whenever we get side products, it takes away from the yield, and chemists would love to have 100% yield in all their transformations. Now, switching to Friedel-Crafts acylation, instead of introducing an alkyl group R, we actually have an acyl group. So there is a carbon-oxygen double bond inserted into the carbon R group here. We can accomplish this. It actually turns out to be a far superior method for functionalizing the benzene ring. We do this again in the presence of a catalyst. In this case, it would be aluminum trichloride. And again, be mindful of the conditions given or necessary for conversion, and then think about what is the electrophile. Well, here we have the mechanism for E+. So here's actually your E+. Okay. And we see that one of the chlorine electron pairs is making that bond. This is again a Lewis base, Lewis acid complex. It activates now the acyl group, and we can remove a net chlorine to now find a very unusual kind of ion, but it does indeed exist. So this is the acylium ion. Be familiar with the term, know how it forms, and also understand that it can be stabilized via resonance. So one of the electron pairs here can be donated towards the carbon, and now we have a triple bond here that is linear, and that will help us understand where to make that new bond. Okay, so this goes back and forth. Here we have the resonance arrow, but basically what we're looking at is now the nucleophile attacking the carbon. Oxygen does not want to make additional bonds. Okay, 3 is the max it can make. And on the next slide, we have the mechanism. So the acylation mechanism starts out. Here's the nucleophile attacking the carbon. We can formulate this either with this ion. We could also use this ion, where we have the positive charge on the carbon and then the double bonded oxygen. Okay, so either way you will get to this intermediate. So here we're using 1. Carbon can only have 4 bonds. We need to break that bond to oxygen, so you end up with this. Again, we have the sigma complex. Here we have 3 possible resonance forms. Then we have to eliminate that hydrogen again to restore aromaticity. I hope that some of the patterns are now becoming very obvious to you. And the more you practice this, the more proficient you will become and will improve your mastery. As before with the nitration reaction, here is another opportunity to overall modify our functionalization. The Friedel-Crafts acylation reaction is often used as a 2-step procedure for introducing the R group. So an acylation followed by a Clemmensen reduction, which means that it is zinc mercury. So this is an amalgam, and then having HCl and heat, will now convert this carbon-oxygen double bond into 2 carbon-hydrogen bonds. Don't be concerned about the mechanism for this. Understand the conditions and how the functionalization changes. The other thing that this does is that, remember how we said that our, let's just say, phenyl R, So any alkyl substituent, as it is here, when we're using the Friedel-Crafts alkylation, we would get polyalkylation. This one here will stop at one substitution because this has an electron withdrawing effect, and there will not be any additional additions to the ring. So the carbonyl group has an electron withdrawing effect. It's an electron withdrawing group. Next slide here describes what I just stated. Polyacylation is generally not observed, which is the major drawback for using Friedel-Crafts alkylation. So here we see it. Here's the withdrawing effect, and you could even draw resonance structures because we could easily take electron density out of the ring and localize it towards the oxygen, which then would not allow this ring to make any nucleophilic attack with any other electrophile. And then here I have another practice question. You may want to pause here, read through it, draw some structures. What I'm asking for is to draw two resonance forms of the electrophile, which is an acylation, which we just discussed, that forms during the reaction. Again, we want to show all the electrons to understand the dynamics. So we have electron pairs here and here. And then we want to understand the role of the catalyst, which is a Lewis acid. Let me see whether I can go back to my ChemDraw program. So this is actually, let me see, is that the correct one? Yes, this is propanoyl chloride. So let me just copy this over or drag this down here into our window. You can use different ways of drawing these structures, but the basic connectivity should be clear to you. If you have trouble with that, you need to go back to chapter 2 for molecular representations and work with this more closely. So as we are looking at the structure, I'll copy it over and manipulate it. We're dealing with a net loss of chlorine. Okay, so since now we have taken away an electron from that single bond, I need to indicate that there's a positive charge here. Oh no, undo. Hold on, I didn't want to erase this. I wanted to have my charge on there. And then maybe let me go and zoom in a little bit closer. So here's our acylium ion. Keep track of those electrons. Let me add electrons. So here I have one set of electrons, another set of electrons, and we want to draw a resonance arrow, which is the double-headed arrow. There we go. And the way we do this, I drew an extra electron pair here. The way we do this is we start out from where there is electron density, so we're using good curved arrows. Let's see, I'm going to try to pick this one. And I'm starting out with the oxygen, and I'm pointing that now in between the oxygen and the carbon. Not so happy with how that looks. Let me rotate this a little bit. There. So we're using one of these electron pairs and reallocating them as a triple bond. And when I do this, I think I'll just do a quick line angle drawing. Now we have a triple bond, and there's an oxygen attached, and I need to make sure I show the remaining electron pair. And because of we're moving electrons and a negative charge, now our positive charge is in a different position. And again, you may need to practice formal charge calculations again or review them if this is a bit murky in your mind. So this would be a good structure. Again, you can go back if this was too fast for you. Let me just copy this over. Copy. And I can paste this in here. So that was what I was asking for, the acylium ion. And having good Lewis structures indicating not just bonding but also non-bonding electrons will help us go down the path. And then always be sure to count carbons. It often happens to me that I lose one or I add one. I have 1, 2, 3 carbons. I have 1, 2, 3, 1, 2, 3. Yeah.